Good morning. Today we're going to talk about significant figures. When you are in science, the number of numbers that you keep in your calculations are really important. Uh, why are they so important? Well, the way we get those numbers in chemistry are by taking measurements. We measure how many people got COVID-19. We take the mass of a piece of metal when we're trying to figure out its density. We carefully record volumes when we're measuring various concentrations of solutions. So we do a lot of measuring in science. So when we use those measurements in calculations, we never want a calculated answer to show a higher level of precision than the tools that were used to make the measurements that contributed to that value. So today we're going to talk about the concept of significant figures, and I'm going to teach you the rules for how you can look at numbers that you didn't take and figure out which ones are significant. So let's start by looking at an example. First of all, before we get too far, you do need to go to modules, and then you see this right here, sig figs and dimensional analysis, slide 24. It's just one slide, but I would like you to open it and then copy it into your digital interactive notebook. You can see it's not very much, it's just one slide. It's kind of where we're starting today. So remember that we can simply use Control A to select, Control C to copy, and then you'll open up your digital interactive notebook and paste it after your last slide, which should be 23 if your numbers are up to date. So pause this for a second, go make sure you've done that, and then we'll resume. So I'm assuming you've done that. So let's go back to our modules. And the slides are here if you want to see them yourself, but I'm just going to go ahead and project them up here for a minute. So, what the heck are significant figures? Significant figures are the numbers that matter when you're doing calculations. In other words, they're the numbers that accurately represent a quantity, a measured quantity that you have taken, whether it's in a lab setting or in real life. So what I'd like you to do is at the top of that first slide, add this statement. Significant figures are the numbers that must be recorded when taking a measurement or solving for a calculation. Let me give you a real-world example. In this image, you can see two graduated cylinders. The first one is just water, and then the second one has a metal cylinder in it, piece of metal. So if you look at this first one, you can see that this curve of water is right here. We call that curve a meniscus. Water does that because it's attracted to each other. The oxygens of one water molecule are attracted to the hydrogens of another. It's kind of the attraction between positive and negative. So when we're looking at this graduated cylinder, you could tell that that curve doesn't quite make it down to this first increment after 20, which would be 21, nor does it make it quite up to the second increment, which is 22. So because this is a tool that requires you to use your eyes to make a visual estimation, you're always supposed to estimate to 1 degree of uncertainty. For example, let's say that Isaac estimated this to be, it's below 22, above 20. Let's say he estimated it to be 21.5. That's fine. But let's say that Luis said, no, that's not 21.5, that's 21.4. Well, they could write down those different numbers, and you might think, wow, that's really bad. They're not agreeing on what that is. Well, one thing, we do estimate things differently as human beings. We don't all look at stuff the same way. But wouldn't you agree that whether you write down 21.4 or 21.5, That's still more accurate than picking either 21 or 22, right? Whenever you have a tool that's visually marked with increments, you personally will have to estimate to one more degree of uncertainty. So for example, if we look at our increments on these graduated cylinders, they're in ones, right? You can see the 5, 10, 15, 20, and then in between are 4 lines that represent the one-step increments. So because this tool measures to the ones, we will estimate to the point ones. Generally, you will estimate to 1/10 of your smallest increment to get to that level of uncertainty. We're going to actually practice this with some tools, but for now, that's just a brief introduction to how we can actually make recordings, make measurements with the right level of precision. So how do we know which digits are significant? I'd like you to take a minute, or more than that, and type these rules into the left side of that slide that you added to your DIN. And then we'll talk about them one to one. So one by one, sorry. So I'm going to ask you to pause this for now, and I'd like you to put this information into your digital interactive notebook. So take a second and pause this and do that. So hopefully you have copied those directions, those rules down. And so now we're going to talk through them. So you know how it is, sometimes you write stuff down, but you have no idea really what you're writing down. You just kind of write it down verbatim, and none of it actually absorbs. So if you look at our first rule says non-zero digits are always significant. So if you look at the number on the right in your digital interactive notebook, you'll notice the first number you have is 1111. And so the point for sig figs is, if we're writing a number down, it's understood that it's part of the measurement. We're not just randomly writing numbers. So in this case, I would say that I have 4 significant figures, because anything that's not a 0 automatically is considered significant. So 1, 2, 3, 4 sig figs. That's the first rule. If it's not a 0, it's significant. The second rule says any zeros between 2 significant digits are significant. So looking back at our examples, you can see we also have this number. So these zeros, as you can see in that, are often called trapped or captive. And what we mean by that is they're trapped between 2 numbers that aren't 0. So this is 110,001, right? Because they're between ones, which are not zeros, they're considered captive and trapped. So in this case, 1, 2, 3, 4, 5, 6, we have 6 sig figs. And the reason those zeros are considered significant is they're considered to be part of the measurement. Why? Once again, you don't just randomly write numbers unless it's implied that it's a number that has meaning, numbers other than 0. So in this case, these are trapped or captive, they count as significant. Our third rule, zeros to the right of significant figures, which are called trailing zeros, are only significant if the number contains a decimal. So before I look at one in your book, let me give you a real world example. When we had, during the quarantine, let's see, million, billion, trillion. During the quarantine, we had a $3 trillion stimulus, right? So in this number, these are all trailing zeros, right? Well, I can write this number two ways because it's dollars, right? I can write it this way, or I can write it this way. Let that focus. So what's the difference? How are these different numbers? Well, they're both 3 trillion, right? But in this one, I added a decimal and 2 zeros. I mean, we're talking about the stimulus, so this is money. Which one of these do you think is the amount that our government spent on our stimulus? Well, this number implies they spent $3 trillion exactly, down to the penny. Most of us understand that when somebody uses a number like 3 trillion, it's probably not exact down to the penny. Instead, it's probably something like 303 trillion, 1,298,563,222, something like that. So in this case, when we see all of these zeros, they're simply placeholders helping us understand this is a huge number. Whereas in this case, when I have that decimal, all of a sudden it adds a whole lot more meaning to those zeros. They are actually a part of a value. Like if you won exactly $3 trillion in the lottery, you would write it like that. That amount of money is going to go into your checking account. Whereas this implies generally. So that's why we have to distinguish between the types of zeros that are to the right of a number. We call them trailing. So you see these have no decimal. So those are all just placeholders to show size. So we would say that this has one significant figure. I always abbreviate significant figure, SF. And then in this one, we would say we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 significant figures. Because zeros are considered significant if there's a decimal somewhere in the number. And the decimal doesn't have to be at the end or in the middle. It can be anywhere in the number, and those zeros to the right will count. So let's look at a couple of other numbers so we can kind of get this explanation, this type of zero stuck in our head. So I am going to change my share to this one so you see it a little bit larger. So moving this up, to the right you have some different numbers. You have 9,900, just making sure I'm getting these right. So we have these various numbers. Now, in all three of these numbers, you'll see the zeros are to the right. So the nines automatically count based on our first rule. As long as it's not zero, it counts. And then for the zeros, we have to look for decimal. If there's a decimal anywhere in the number, those zeros are significant. If there's not a decimal, they aren't. So in this case, the nines are significant, but because there's no decimal, the zeros are not. So we would say that this first number has 2 sig figs. On the second one, the nines count. This time there's a decimal somewhere in the number. So we're going to count those zeros as significant too. 99.00, same story. The nines count automatically, the zeros are to the right, and because there's a decimal, they count. Now this is a small number, right? 0.9900. The nines count automatically, but once again, because there's a decimal in the number, those trailing zeros will also count. That decimal is implying that they are a part of a measurement, and that's why we included them. So, just a quick recap. First rule, if it's not zero, it's significant. Second rule, If the zero has numbers to the left and to the right that aren't zero, they're considered trapped or captive, they're significant. And then the third rule that we've looked at so far, the zeros to the right can be significant, but only if there's a decimal in the number. If there's not a decimal, the ones to the right are not counted as significant. So let's look at our last type of zeros. We've looked at zeros in the middle and zeros at the end, so now we need to look at zeros in the beginning of the number. So rule 4, let's go back to that for a second. Rule 4 says that zeros to the left of significant figures, which are also known as leading zeros, are never significant. So why are zeros to the left not significant? Well, just like zeros to the right, when there's no decimal, zeros to the left are about showing how big or small something is. So, like when I was looking at 3 trillion, let me go back, sorry, just splitting my screen. When I was looking at 3 trillion, those zeros weren't significant because there was no decimal. They were just showing me how huge that number is. Likewise, if I have a number that's really small, those leading zeros, the ones to the left, are simply showing me how tiny that number is. So once again, they're placeholder zeros. They're not really part of the measurement. So leading zeros are never significant. So we would say that this number only has 2 sig figs. And all of these, I'm putting X's here to remind myself they're not significant. They matter. Let's not confuse significance with mattering. They matter because they show how tiny the number is, just like these matter because they show how huge the number is. But they don't communicate a measurement. They just communicate size. So let's look at the ones that you have in your book, in your DIN slide. And you'll notice that we have one that's kind of in this category, 0.000999. So the 9s count because they're not zeros. But these are leading zeros, so they will not count. So we will say this has 3 sig figs. Now let me clarify something. Sometimes people see this decimal and say, but wait, those zeros are after that decimal. You said that zeros count when they're trailing and there's a decimal. Well, these aren't trailing. They're still in the front of the number. Any of the zeros to the left are leading, whether they're on the left of the decimal or the right, and we don't count them as significant. So we have 2 other numbers on this slide that we have not looked at yet, so let's go ahead and look at those. The first one is 8080800, sorry, there's a lot of zeros here, decimal. So off the bat, we know which 3 count automatically? The 8s. So what kind of zeros are these 2 zeros? Do you recall of the groups we had up here? Well, yeah, these are trapped or captive zeros. So are we going to count them? Yes. You can really use whichever word speaks to you more, captive or trapped. As long as you can identify they're significant, it doesn't matter. Now, what kind of zeros are these? Are they leading or trailing? Well, these are trailing. And did I write a decimal in the number? Yeah, right there. Now, that may look weird to you to have a decimal at the end of a number, but we do that frequently in science to show that that zero is actually a part of a measurement and not insignificant. So because these are trailing and there's a decimal in the number, I will also count that. So this number is going to have 8 sig figs. The other number that's on here is 0.00567 So this number actually has 3 types of zeros. What do we call the ones to the left? They're leading zeros. This one would be captive. And then this last one would be trailing. Do leading zeros count? No. They're there to show how small it is, but they're not considered a part of the measurement. The 5, 6, 7, and 8 count because anything that's not a zero counts. This one's captive, so it counts. And this one is trailing. And because there's a decimal in the number way up here, it will count. The decimal can be anywhere in the number for the zeros to the right to count. So this one would have 6 sig figs. So those are our rules. There's 2 other things though that I want to remind you of. Because that was really just the first 4 rules, right? So when we're talking about when we're talking about numbers like this, the first 4 rules apply to numbers that are measurements, lengths, masses possibly, densities, joules, any of those values that we've used, these would apply to because we measure things. But some numbers aren't measured. For example, in your class, if I counted the students, I could count the students and say, oh, currently between the people that are in person and the people are at home, I have 27 students. I've counted them. I didn't measure you. There are exactly 27 students. If I have eggs, a dozen eggs, I have 12 exactly. I can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Numbers that are counted are considered perfect numbers. And what we mean by that is they're never going to limit you for sig figs. If I said I had 27 students, I could literally put 27.0 to infinity, right? An infinity number of zeros. That's exactly how many students we have. So for perfect numbers, we say that they have an unlimited number of sig figs. You'll understand a little bit more what that means when we start talking about how we do math with significant figures. And then the last thing that I need to bring out is when you have scientific notation, the scientific notation part, the 10 to the x, 10 to the third, or 10 to the negative fifth, or 10 to the eighth, that part is not significant. Why is it not significant? Well, it's actually just a different way to represent trailing zeros and leading zeros. It's just about size. So it is not considered a part of the measurement. So let's look at what I mean by that just really quickly. So let's say that I had this number. Okay, 3,000. If I wanted to write that in scientific notation, I move the understood decimal 1, 2, 3 until there's one number to the left of the decimal. So this would be 3 times 10 to the, I'll use this different color, 1, 2, 3. So this is 10 to the third. Likewise, if I had point 0.003, I move the decimal 1, 2, 3. See, I always want to move it until there's one number that's not 0 to the left. So because I had to move this 3 places to the right, this is 3 times 10 to the negative third. Now, going back to look at the original numbers, I didn't have a decimal in this number, right? I had 1 sig fig. So that 10 to the third simply is simply representing those 3 insignificant zeros. Likewise, in this number, these were leading zeros. They don't count for significance. So that exponent of 10 to the negative third represented leading zeros. So because the scientific notation simply represents place-holding zeros that aren't significant, it too is not significant, Just to reiterate though, not being significant doesn't mean it doesn't matter. It matters absolutely to show size. It just doesn't matter as far as it being communicated as part of a measurement. So whenever you see scientific notation, if I had this number, for example, this would communicate that although this is not significant, this is, and then what kind of zeros are these? Well, they're trailing in a number with a decimal. So this one would have 3 sig figs, but I'm not counting that. These all have 1 sig fig. So what I'd like you to do is to go back to Canvas, and I would like you to open up Sig Fig and Dimensional Analysis Practice. And I would like you to try question 1. Just do that on your own paper. Just number 1A, 1B, 1C, 1D, 1E, 1F. And we will go over that in a few minutes together. So you're done having to listen to me in video form for a little while. But I'm going to let you go ahead and try that. Do it on your own paper, and then we'll talk through the answers to make sure you are getting it.